Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we were discussing about the unbalanced voltage operation of induction motor. We saw that when the voltages are unbalanced, the torque and power both are reduced and we have to derate the motor, which means the motor cannot be operated at the rated power, it has to be operated at a reduced power. Now, let us see today, suppose one phase is open circuited, just one phase out of 3 phase, one phase is open circuited, that is called single phasing. Single phasing is a special case of unbalance. Let us see what happens in case of single phasing. What happens here is that we have the 3 phase stator, phase A, phase B and phase C. Let us say this is phase A, phase B and phase C, and we have the rotor which is a cage rotor, and these 3 are connected to the power supply. So, we have the supply which is supplying these 3 phases. So, out of these 3 phases, one phase is open circuited. Let us say this phase is open circuited. The C phase is disconnected, that is called single phasing. In case of single phasing, it is a case of unbalance, and we can analyze it later that when we have single phasing, the positive sequence voltage is equal to the negative sequence voltage. When we have single phasing, the positive sequence voltage equal to the negative sequence voltage, and we have IN is equal to minus of IP. Now, when we have IN equal to minus of IP, we can draw the equivalent circuit. In this case, of induction motor. So, we have 2 network here, one is a positive sequence network which is given by the circuit, and we also have a negative sequence network . And the voltages are equally divided. So, what we expect here is the following, that we have something very similar, and we have the resistance here R s, the XS is the resistance, the reactance here, and Xm is the magnetizing reactance, Xr prime is the rotor reactance, the leakage reactance, Rr prime by S, P is a positive sequence slip, and then we have a negative sequence circuit which will be connected in series. So, this is the resistance, this is the reactance of the stator, the magnetizing reactance, the reactance of the rotor Xr prime, and the rotor resistance divided by the negative sequence slip. So, this voltage which is applied here is the voltage which we can calculate what is this voltage. Now, one thing has to be noted here, that when we open circuit one phase, it is basically a single phase induction motor. So, we have a forward field and we have a backward field. So, this is no longer a 3 phase machine, because one phase is here open circuited. So, this is a single phase induction motor. So, that is why we call this to be a single phasing of induction motor. So, we have a forward field which rotates in the forward direction, that is phi f, and we have a reverse field which rotates in the backward direction, which is phi r, and this field are initially of the same magnitude. So, the speed of one is omega ms synchronous speed, and the other speed is minus of omega ms, because this rotates in the opposite direction. So, the speed of the rotor is in one direction. So, the rotor is rotating, let us say, in the forward direction, that is omega m. So, we can calculate two slips, one slip for the forward field or the positive sequence field, other slip is for the negative sequence slip or the reverse flux. Now, in this case, what is SP? This is the positive sequence slip. We have the positive sequence field is omega ms minus omega m by omega ms, that is equal to simply S. What about the negative sequence slip? The negative sequence field is rotating in the opposite direction, which is minus of omega ms. So, if we substitute the synchronous speed by minus of omega ms minus omega m by minus omega ms, what we get here is omega ms plus omega m by omega ms. We will just do some readjustment, 2 omega ms minus of omega ms minus omega m by omega ms, and this we simplify as 2 minus S. So, what we get here is that the positive sequence slip is S, simply S. So, we can write here R r by S, and the negative sequence slip is 2 minus S. So, this is R r by 2 minus S. So, we have the positive sequence current, which is I p, and we have the negative sequence current, which is I n. They are equal and opposite, because we have single phased one of the phases. So, this becomes a single phase induction motor. What about the torque speed characteristic? Now, we will see what happens to the torque speed characteristic. So, we have the speed in the y axis and the torque in the x axis here, the origin in this case, and we have two fields. One is a forward field. So, we have a forward positive sequence torque here, which goes like this, and the synchronous speed here is plus omega ms, and then we have the reverse direction. We have the speed in the negative direction is minus of omega ms, that is the negative synchronous speed. This is the x axis. So, the negative torque, the negative sequence torque will verily be equal, something similar to the positive sequence torque. So, this torque is the positive sequence torque. What about the negative sequence torque? So, this will be just quite similar to that in this particular fashion. So, this is the negative sequence torque. So, this we can call to be T p, and this is T n, as we have derived earlier. Now, the net torque T is the sum of the positive sequence torque plus the negative sequence torque. So, if we add these two, one is a positive torque, other is a negative torque. So, the net torque will have the following nature. So, this is the net torque, which is a reduced torque here, and since we have positive and the negative sequence field are quite equal here, this and this is same. So, we have 0 torque when the speed is 0. So, this is the torque speed characteristic, which is the net torque of the single phase motor. This is the net torque, which is T. So, we see that the starting torque is 0. So, if we have a single phase machine, the single phase machine cannot start on its own, because there is no starting torque here. The starting torque is 0. This axis is the speed axis. So, speed is 0 here, but as the speed increases, maybe in the positive direction, we see that the motor picks up speed and settles down to the full value. Suppose the motor was earlier running at certain speed. Let us say that the motor was running earlier at this speed, this is the operating point of the motor before it was single phased. So, when this is the operating point of the motor before it was single phased, now the motor is single phased here. So, the torque will drastically reduce, because corresponding to this speed, the single phase machine will be developing this torque. And if the load is fixed, let us say, if the load is fixed, so the characteristic is decided by the intersection of the load with the motor characteristic. Say for example, if this is our load torque TL, earlier we are operating somewhere here, now it is single phased, we will be operating somewhere here. So, the motor continues to rotate. When we single phase an induction machine, it continues to rotate, but the speed will be little bit reduced. So, speed will be close to synchronous speed, but it is reduced from the earlier value. And here we are assuming that the rotor resistance is low. So, the speed is reduced, but the motor continues to rotate with a reduced power, because here the torque is reduced, the speed is also reduced. So, we conclude here that torque and power are reduced, are less for a single phase, are less for a single phased motor compared to a normal 3-phase motor. So, this runs actually at certain value of slip, but the power is reduced, which means the torque and speed both are reduced. Now, let us see that we have already discussed about the motoring operation. So, we will see what are the various types of braking of induction motor, because it is an AC machine. So, braking means we mean to say that it is electrical braking. How can we make the motor function as a generator, so that the power can be fed back to the supply, or it can be dissipated in some resistance. So, we will be discussing the braking of induction motors. Now, when we talk about braking, we have various types of braking. The first one is called regenerative braking. Where the power is fed back to the supply. The second type of braking is called plugging. This is also known as reverse voltage braking. Reverse voltage braking. third type of braking is called the dynamic braking. Dynamic braking has got a few classification. The first one is called AC dynamic braking. The second type of dynamic braking is called a DC dynamic braking. There is also a type of braking which is called self excited capacitor based braking. So, these are the few types of braking that we have in case of a induction motor. So, let us try to understand what is a regenerative braking. So, when we talk about regenerative braking, what happens is the following. Let us redraw the torque speed characteristic of an induction motor. This is the speed axis and we have the torque axis here and this is the origin. Now, the torque speed characteristic is of this nature. So, this is the first quadrant. So, in the first quadrant we have the torque speed characteristic of a normal induction motor. We have the maximum torque here, this is T max, and we there is some slip, this is the synchronous speed omega ms, and this is the speed equal to 0. So, if we write the slip in this case, slip is 0 at synchronous speed and slip is 1 at starting. So, now if we make the motor rotate at a speed higher than the synchronous speed, what happens? If the speed goes higher than the synchronous speed, this characteristic enters into the second quadrant. So, this is the second quadrant behavior of the induction motor. Now, in the second quadrant, which is this one, the speed is higher than the synchronous speed. So, we are increasing the speed higher than the synchronous speed. So, in that case the slip here becomes negative. So, this is for negative value of slip. So, when the slip is negative, torque is also negative, and here the power is also negative, which means the power is fed back to the supply. Now, how can we make the motor speed higher than the synchronous speed? Now, if we have a motor here, if we have a motor and the motor is fed from, let us say, inverter, and this inverter is VV VF, we have a DC source which convert this into AC, VV VF inverter. So, VV VF stands for variable voltage, variable frequency. So, we have the DC voltage here, and then by using an inverter we can vary the frequency of the output voltage, also the voltage of the output voltage. So, when we vary the frequency, we make the frequency somewhat reduced. So, when we make the frequency less such that the motor speed is higher than the synchronous speed, let us say this is our speed here. So, this speed is higher than the synchronous speed, we get a negative torque, which means we enter into the second quadrant and the energy flow reverses. This is our induction motor I m, and this is the inverter. So, the motor is now behaving as a generator, which means the energy or the power flows back to the supply. So, the power from the induction motor, which is functioning as a generator, is fed back to the supply. The supply is a DC supply. So, the battery or the DC supply is charged. So, this is called regenerative braking, which will require a variable voltage and variable frequency source or a VB/VF inverter. Now, let us see the second type of braking, which is called plugging. Plugging or reverse voltage braking. Now, in case of reverse voltage braking, what happens is the following. Now, we change the phase sequence of the supply, which is applied to the stator of the induction motor. So, when we change the phase sequence, the direction of the rotating field changed. So, which means the voltage sequence is reversed, and that is called plugging. So, in this case we have the induction motor, and which is fed from a supply. So, what we do here, we change the phase sequence of the supply. Suppose this is A, B and C of the machine. So, what we do here is that we change the phase sequence of the supply. So, this is the supply here, supply is A here, and this is B and this is C. So, instead of supplying A, B, C to our machine, so we are giving B, A, C. So, we have the change in the phase sequence, this is the induction motor. So, if we change the phase sequence, the direction of the rotating field gets changed, and that is how we get plugging. Let us draw the torque speed characteristic. This is omega m versus torque here, omega m in the y axis and torque in the x axis. So, this is our normal operation of the machine. So, this is the first quadrant, and we have the second quadrant. So, this is the positive synchronous speed omega ms plus omega ms. Now, when we change the phase sequence of the motor, the synchronous speed reverses. It means it becomes minus omega ms. So, we get a negative synchronous speed, which is here, and this is minus omega ms. Now, we again draw the torque speed characteristic here. So, this is the torque speed characteristic. This. So, and if we have a slip ring induction machine, we have the provision of introducing resistance in the rotor. So, we have the rotor circuit in which we can insert the resistance for a slip ring induction motor. So, this is possible if you have a slip ring induction motor. Slip ring induction motor. For slip ring induction motor, we introduce the rotor resistance. So, when we introduce the rotor resistance and go on varying the rotor resistance, our characteristic for negative synchronous speed will change like this. This is for a higher value of resistance and so on. So, this is say for example, this is for R1 prime and this is R2 prime. So, what we are trying to do here, we are trying to vary the rotor resistance of induction motor. So, in this case R2 prime is higher than R1 prime. It means when we insert rotor resistance, the characteristic will be different here, and this will be shown by the dotted line. Suppose the motor was earlier operating at this speed. Okay. Now, when we immediately change the phase sequence, the characteristic which is the normal characteristic. Okay. Say for example, this characteristic is called A and this is say B and this characteristic is C, let us say. So, the characteristic A will be left. This the motor will change from the characteristic A to let us say the characteristic B. So, it means the mechanical speed, when we are changing the connection, the speed being a mechanical variable, the speed cannot change immediately. So, the speed remaining constant, torque will immediately become negative. So, it means this will change from 0.1 to 0.2. So, the operating point of the motor will change from 1 to 2 and then the torque is negative. So, the machine will decelerate, machine will reduce the speed, so the speed will be reduced. So, it basically goes like this, and at 0 speed the torque is still negative. Unless we open the connections here, this will reach a 0 speed and accelerate in the negative direction. So, we have to stop the motor. So, we have to immediately remove the excitation, remove the supply. Now, if we introduce more resistance, we will have more braking torque. So, instead of reaching 2, we will be reaching 3. The characteristic will be corresponding to C. So, in that case, we will be following this characteristic for an increased value of rotor resistance, and even at 0 speed we have quite a amount of negative torque. Unless we remove the supply, we will reach the third quadrant, which is for the reverse motoring, and if you want to stop at 0 speed, we have to remove the supply. It means we will come back to 0 speed here. So, for plugging, the current is extremely large because we are reversing the phase sequence. So, it is mandatory to put rotor resistance. So, plugging is attempted only in case of a slip ring induction machine. So, in this case we have to insert sufficient rotor resistance to limit the current. Now, let us see the third type of braking, which is the dynamic braking. The dynamic braking, as we have already seen, is here the kinetic energy is dissipated in the resistance. The kinetic energy of the motor is dissipated in the resistance. So, we have various types of dynamic braking. They are AC dynamic braking, then we have DC dynamic braking, and the third one is self excited induction motor, induction generator based braking. So, all this braking aims at the dissipation of motor kinetic energy in some form of resistance, may it be rotor or may it be some external resistance. So, the energy of the motor, the kinetic energy of the motor is dissipated in some resistance. So, we stop here for today's lecture. We will continue this dynamic braking of induction motor in the next lecture.